All right, 10.3.1, irrational numbers and surds. Rational numbers we've looked at before. They're part of our real numbers. Real numbers, remember, anything on a number line. Rational numbers, the hint in the word ratio there, you can see I've already underlined it. Ratio can be expressed as a ratio, as a fraction, involving two integers, two whole numbers, positive or negative. These rational numbers can also be terminating or recurring decimals. We all know, say, 0.3 recurring is the same as 1/3. And terminating decimals, they've given an example there, 1.6. 1.6 would be the same as 16 divided by 10, or 8 over 5. You could write it in a number of different ways, but definitely can be expressed as a rational number. Irrational numbers, the decimals don't terminate, they don't repeat, they just go on forever with no pattern. What are examples? Square root of 3, negative 2 root 7, pi. You can see the other examples there. All these numbers, non-terminating decimals, they are irrational numbers. Now, irrational numbers are split up into two categories. What are the two categories? Well, the ones we're going to look at today, and in this chapter, are surds. Surds use the root sign, or sometimes called the radical sign. So we'll call that a root sign, but often you'll see online it's called a radical sign as well. These turn up as solutions to polynomial equations. So for example, if I had x squared equaled 2, then I would get x equals plus or minus root 2. So you can see that was a polynomial equation. It had a power of x greater than 1. And the solution was a square root, or involves a root. It could involve a cube root as well. If I had x cubed equals 11, then x would be the cube root of 11. Again, involving a root sign, there's no number that's a nice cube root of 11. That goes on forever. That's an irrational number. That's a surd. What are the other ones called? Ones like pi, other numbers like e, Euler's number. Well, they're transcendental numbers. And they are not solutions to polynomial equations, but also have non-repeating, non-recurring decimals. Enough about them for now. What are we going to do with these surds? Well, the first thing we've got to be able to do is simplify them, and then we've got to be able to do some operations with them. To simplify them, you just look for square factors. Factors which are perfect squares that are factors of the larger number, and then you separate the surd out. It's going to be much easier if we see an example. They've done it there with A and B, but that's not really easy to see. So let's have a look at an example of simplifying a surd. Let's pick 75. So my first step, remember, is to look for a number that's a perfect square that's also a factor of 75. Now we're looking across the list here because they've provided us with a list of perfect squares, and you'll see there 25 is a perfect square. It's 5 squared, and it's also a factor of 75. So I can merely rewrite this as root 25. How many 25s make 75? 3. Now I see why we do that. Root 25 can be simplified, can't it? We all know the square root of 25 is 5 root 3. Now notice here, even though negative 5 times negative 5 equals 25, I didn't say plus or minus 5 here. Plus and minus turns up when you're solving an equation involving a squared number, a squared factor like x squared or x cubed. The square root of a number is defined as being the positive number. If I want to have negative square root 25, I would write it like that, and that would equal negative 5. That's just a little distinction, but if you just have a square root on its own, it is positive. All right, enough about that. Let's have a look at another one to simplify. Let's simplify root, 198. So I need to look for factors that are perfect squares that go into 198. Now, you may or may not be able to think of one that goes into 198 straight away. You should be able to remember the test to see if 4 goes into a number. If 4 goes into a number, the last 2 digits are divisible by 4. Well, I know 4 goes into 100, so that's not going to work. Now, I do know of a number that goes in there, but let's see if we can simplify this a little bit. Sometimes it's easier to break that number 198 up. So I'm going to take that 198. I know, love the touch screen, that 2 goes into 198. How many times does 2 go into 198? Oh, that'd be 99 times. Now 2 wasn't a perfect square, but that's okay. If I couldn't identify a perfect square, you could have used your calculator to find it. If you couldn't, you can still try and find one now. And now it's become a bit more obvious that 9 goes into 99, doesn't it? Those of you who remember the rule for divisibility by 9 would have seen that 1 plus 9 plus 8 was divisible by 9, so 9 would have gone into it. But if you can't see it straight away, just try and simplify it a little bit and then see how you go. So now I've got root 2 by root 9 by root 11, because 99 is 9 times 11. Now this one, the root 9, can be simplified. I'm going to make that 3. Root 2 times root 11 cannot be simplified, but 2 11s are 22. So I'm going to make it 3 root 22, and that's the simplification of root 198. That's all there really is to this exercise. The first one's pretty nice. Get stuck into those level 1 and level 2 diagnostic questions. When do these other things turn up? When were they first really discovered? Well, let's have a look. This will little bit of history here, and I know that this turns up in the first exercise somewhere. Let's say I want to find the length of the hypotenuse when I've got this side is 2 meters and this side is 5 meters. Well, using Pythagoras' theorem, the square on the hypotenuse is equal to the sum of the squares on the other two sides. So I can do that. H squared equals 25 plus 4. H squared equals 29. Therefore, H equals root 29. Why am I not doing plus or minus? Well, I know in this case it's a distance. It's got to be positive. So I don't need to worry about negative root 29 being the distance. All the questions in this first exercise are just like that. Get stuck into them, do the hot maths, and let's move on. We should be able to go through the first few exercises in this chapter really quickly. Have fun, guys.